Welcome to the third lecture of the Marketing and Customer Support module. The topic of this lecture is blockchain and sustainability. To understand the content of this lecture, we recommend that you have previously watched the lectures of Module 1, Introduction to Blockchain Methodology, and Module 3, Fundamentals of Blockchain and Distributed Ledger Technology. The learning material is designed to provide you with important future skills, see Ehlers 2020, to gain the ability to effectively manage or develop blockchain services and processes. This lecture is all about sustainability. We start with the learning objectives of this lecture and the module. Then we will give you an overview of the global agreements on sustainability and development goals. Afterwards, we have a look at the ESG factors of responsible investment of Bitcoin currency and the different consensus mechanisms. We will close this lecture with a short conclusion. This slide shows an overview of the knowledge, skills, responsibilities, and autonomies you will acquire in this lecture. Learning objectives. In marketing, the communication of responsibility and the ethical evaluation is a very important skill. After this lecture, you should have an awareness of customer success design. You should be able to create awareness of blockchain use among broader audience and have the capability to critically analyze and ethically evaluate marketing strategies. Sustainability and global agreements. When we talk about sustainability, we must first be aware of the current situation. Here is a brief introduction to the Paris Climate Agreement of 2015 and the Sustainable Development Goals. The Paris Climate Agreement of 2015 and its status as of 2022. The Paris Agreement is a treaty under international law concluded by 195 parties on the occasion of the United Nations Framework Convention on Climate Change, otherwise known as the UNFCCC, with the aim of protecting the climate as a successor to the Kyoto Protocol. The convention was adopted on the 12th of December of 2015 at the UN Climate Change Conference in Paris and provides for limiting man-made global warming to well below 2 degrees Celsius above pre-industrial levels. However, studies to date suggest that even the 2 degrees Celsius target may not be sufficient to safely prevent irreversible feedbacks from tipping elements in the Earth's system, which would then move the Earth's climate into a hot period several degrees above today's temperature. Climate tipping elements are critical, large-scale components of the Earth's system, which are characterized by a threshold behavior. These systems appear to remain stable with increasing global temperature, but starting at a particularly global temperature threshold, very small additional disturbances can tip them into a qualitatively new state. If you imagine a pencil being slowly pushed further over a table edge, at first, nothing happens. Then it falls. The threshold behavior is often based on self-reinforcing processes which, when tipped, can continue without further external forcing. It is thus possible that a component of the Earth system remains tipped even if the background climate falls back below the threshold. The transition resulting from the exceedance of a system-specific tipping point can be either abrupt or gradual. Crossing single tipping points has severe impacts on the environment and threatens the livelihood of many people. There is also the risk that, through feedback loops, further tipping points in the Earth system are reached and a domino-like chain reaction is initiated. On the picture, you can see the different identified tipping points at which the level of global warming they become likely to be triggered. In this context, the IPCC's special report on 1.5 degrees Celsius global warming of 2018 also warns of irreversible consequences, as well as of a further increase in extreme heat, heavy precipitation and droughts, and an additional rise in sea level. The objectives of the convention is set out in Article 2, improving implementations of the UNFCCC as follows. A. Limit the increase in global average temperature to well below 2 degrees Celsius above pre-industrial levels, making efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels. The pre-industrial level is the average of the years between 1850 to the 1900s. This should significantly reduce the risks and impact of climate change. B. Increase the capacity to adapt to the adverse effects of climate change, promote resilience to climate change, and promote development that is low in greenhouse gas emissions while not threatening food production. And C, make financial flows compatible with the pathway towards low greenhouse gas emissions and climate resilient development. Necessary measures. Translated into scientific terms, the agreement means meeting the 2-degree target with a probability of more than 66%, while maintaining a 50% chance of meeting the 1.5 degrees limit. This results in a fixed CO2 budget, i.e., an upper limit for emissions that may still be released at most. According to this, global greenhouse gas emissions must peak by 2020 and at the latest, and be halved per decade after. This means that emissions must fall from 40 billion tons in 2020 to 20 billion tons in 2030, to 10 billion tons in 2040, and 5 billion tons in 2050. In parallel, the share of carbon dioxide-free energy sources must be doubled every 5 to 7 years. Moreover, negative emissions, i.e., the active removal of carbon dioxide from the atmosphere, will be necessary for this scenario even before the middle of the 21st century. According to a calculation by Alan Fawcett et al. From 2015, we have an 8% chance of a global warming level of only plus 2 degrees Celsius of pre-industrial levels if the previous international and national ambitions and consensus in the Paris Agreement are met. More likely, there is an increase to between 3 to 4 degrees Celsius from pre-industrial levels in the next 80 years. The ICPP climate report has shown how natural disasters increase when the future of global warming levels change. These figures show that extreme temperature events, which normally occur only once every 50 years, will occur 13.9 times more at plus 2 degrees Celsius global warming levels. At 4 degrees Celsius, they are even 39.2 times more frequent, and thus more frequent than every second year. The Sustainable Development Goals were developed in parallel to the Paris Climate Agreement. The 2030 Agenda for Sustainable Development, adopted by all United Nations member states in 2015, provides a shared blueprint for peace and prosperity for people and the planet, now and into the future. At its heart are the 17 Sustainable Development Goals, also known as SDGs, which are an urgent call for action by all countries, developed and developing, in a global partnership. The 17 SDGs are no poverty, zero hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable and clean energy, decent work and economic growth, industry, innovation and infrastructure, reduced inequality, sustainable cities and communities, responsible consumption and production, climate action, life below water, life on land, peace, justice, and strong institutions, partnerships for the goals. There are cross-cutting issues and synergies between the different goals. With regard to SDG 13 on climate action, the IPCC sees a robust synergies, particularly for the SDGs 3, health, 7, clean energy, 11, cities and communities, 12, responsible consumption and production, and 14, oceans. Each goal typically has 8 to 12 targets, and each target has between 1 and 4 indicators used to measure progress towards reaching the targets. The blockchain technology in this regard has a massive impact on the goals for energy and economics. As the previous slide showed, we already have a code red warning for the climate change goal. Especially the energy released related to CO2 increase is related, among other things, with energy-intensive technologies such as blockchain. ESG factors of responsible investment practices. What do these goals mean for blockchain technologies, its communication, and further development? The digital currency Bitcoin is known for its energy hunger and associated carbon footprint. Investors, however, must not neglect further environmental, social, and governance issues related to digital currencies. Therefore, we urge the adoption of a more comprehensive view in assessing the externalities of investment in Bitcoin and other cryptocurrencies. Annualized total Bitcoin footprints. For the environment, the oldest cryptocurrency is no savior, and with increasing popularity, the problems are also mounting. On the one hand, the enormously high energy consumption of the Bitcoin network causes corresponding emissions of the greenhouse gas CO2. In addition, ever larger amounts of electronic waste are also being produced. In order to curb the energy input, there are various ideas of green energy as the basis for the mining projects. The main problem is that the mining farms need electricity all the time, which is why photovoltaic and wind power are only suitable to a limited extent because of the fluctuating generation. According to DG Economist's calculations, blockchain's annual carbon footprint is 72.22 mt CO2. This is comparable to the size of Austria's carbon footprint. The annual consumption of electric energy is 129.48 terawatts, which is the same as Norway, and the amount of electronic waste is comparable to that of the Netherlands. Environmental, social, and governance, also known as ESG issues, have become a pivotal factor in economic and financial markets. Emissions, however, only comprise one of the three ESG factors of responsible investment practices. Social and governance factors have received limited attention in previous academic literature on cryptocurrencies. So here's an overview of the other ESG factors we want to review in regard to the sustainable impact of blockchain. Environmental factors. The environmental factors include energy consumption, greenhouse gas emissions, material used, and disposed waste. Bitcoin's energy consumption mainly results from a process known as mining. Bitcoin miners update the underlying digital ledger, known as blockchain, by validating transactions and adding them in new blocks. Because the Bitcoin network is an open network, anyone can join this process if they have suitable computer hardware. The Bitcoin protocol provides an incentive to participate because the creators of new blocks receive a reward in Bitcoins. Creating a new block is, however, intentionally computationally expensive. Until now, there has been no guidance on how to allocate the carbon footprint of Bitcoin among investors. One option would be to adapt the greenhouse gas GHG protocol, which is the world's most widely used standard to account for corporate emissions. For equity investments where the reporting company has no financial control or significant influence over the emitting entity, the GHG protocol prescribes an equity share approach that proportionally allocates emissions to investors. Although Bitcoin does not represent an equity investment, most people buy Bitcoin for its investment value. Because Bitcoin is a decentralized system, investors have neither control nor influence over Bitcoin. They only control their obtained share. Carbon emissions are not the only environmental impact of Bitcoin. Bitcoin miners use considerable quantities of highly specialized and short-lived mining hardware that cannot be repurposed. The entire network generates as much electronic waste, which results in an electronic waste footprint. This equipment is primarily made of aluminum, copper, iron, and rare earths. Low waste collection and recycling rates in countries with high mining activity create the risk of toxic chemicals and heavy metals leaching into soils and causing air and water pollution. Social factors. The social factors include societal security, labor practices, equality, and health. Although leading investment banks currently only consider the environmental factors of Bitcoin in their ESG assessments of this digital currency, recent research has examined the social impact of Bitcoin. Recent events have drawn attention to how Bitcoin could affect societal security. For instance, Bitcoin mining could enable countries to circumvent economic sanctions imposed to increase international safety. Additionally, the soaring demands for mining hardware is exacerbating the global shortage of computer chips. This shortage could prevent automakers from manufacturing more electric cars, because electric vehicles require far more chips than do traditional combustion engine vehicles. The chip shortage also constrains the supply of laptops, mobile phones, and other electronic devices. If this situation continues, it could impact the availability of equipment required to work from home. Remote working has become a vital strategy in preventing the spread of the coronavirus disease from the 2019 pandemic, reducing the need for heating and cooling commercial properties and reducing gasoline use for transportation. Bitcoin mining could also significantly affect societal security due to its impact on electrical grid stability. Power outages in Tehran and Sukhumi have illustrated how local communities might suffer due to the popularity of Bitcoin mining. Bitcoin miners typically operate 24/7, year-round, but higher baseload demand will reduce grid stability during periods of peak demand. Bitcoin could also be linked to illegal financial activities. Although criminal use of the network for money laundering or other illicit transactions is limited and comprises only 0.3% of the overall transaction value, Bitcoin is characterized by an absence of trusted third parties, a central issuing authority, or proper regulation. As such, Bitcoin offers no comprehensive nor clear legal protection for its users. Critics argue that Bitcoin offers significant opportunities for theft and fraud, and that cryptocurrency markets are prone to price manipulation. When examining the social impact of Bitcoin, labor practices should also be considered, because Bitcoin mining might occur in locations that violate international working conditions standards. A significant number of Bitcoin miners are found in the Chinese province of Xinjiang because of its abundance of cheap coal-based power. In April of 2021, an incident in a local Xinjiang coal mine interrupted one-third of the entire Bitcoin network's computational power. ESG-compliant investors should therefore consider potential conflicts of interest, because coal mines in Xinjiang have been mentioned in the context of forced labor. Xinjiang has repeatedly been criticized for hosting detention camps for Muslim minorities such as the Uyghurs. Of all the social aspects discussed in this section, Bitcoin's effect on a healthy lifestyle is less concrete. However, the production of electricity required to run the Bitcoin network has been linked to air pollution, which directly impacts human health. Governance factors. Governance includes aspects such as transparency, competitive behavior, indirect economic impacts, and taxation. Governance might seem like the least relevant ESG factor that concerns Bitcoin, because by design, Bitcoin is not controlled by any entity. However, multiple parties have a significant influence on Bitcoin and its surrounding ecosystem. First and foremost, the Bitcoin network is based on open source software. Anyone can run, change, fork, or develop code that enables participation in the Bitcoin network. Although several different implementations exist, 95% of all publicly available nodes in the network run Bitcoin Core, the original software written by Satoshi Nakamoto. A small group of developers manages the corresponding GitHub repository, and potential updates are discussed via Bitcoin improvement proposals known as BIPs. However, because Bitcoin Core has no automatic updates, network participants decide which code they run on their node. A small number of privately owned mining pools control the majority of computational power in the Bitcoin network, which endangers competitive behavior. This concentration of control enables large actors to form new points of control within the blockchain infrastructure, because these parties have the power to accept or reject BIPs. Other actors in the ecosystem, such as exchanges, managers of fiduciary funds, or influencers with huge numbers of followers, can easily alter beliefs and investment behavior, which could lead to abuse of market power. Such actions affect the network's reliability and integrity and threatens the confidentiality of information about network users. Further, Bitcoin might enable tax evasion. Depending on the jurisdiction, capital gains on Bitcoin or other cryptocurrencies might be subject to taxes. Because of Bitcoin's decentralized nature, and because a single Bitcoin cannot be attributed to a country, the owner of Bitcoin assets has the autonomy to decide where and how to file any related capital gains. Consensus mechanism. The infamy of blockchain lies mainly in its high energy consumption as a result of the proof of work POW consensus mechanism it mostly employs. The consensus mechanism is an integral facet of the blockchain for achieving trust among nodes. Although other consensus mechanisms have since been introduced to either mitigate the shortfall of POW or better suit some blockchain use cases, These consensus mechanisms are both with benefits and shortfalls, which invariably affect the blockchain's efficacy and sustainability. Consensus algorithms. There are now many different consensus mechanisms for the blockchain. Probably the best known are proof of work and proof of stake. Proof of work, also known as POW, was developed to alleviate double spending in the network. A proof of work demands that nodes that verify transactions, known as miners, must perform a complex computation to assert the validity of entities in the network. In Bitcoin, mining nodes compete to validate transactions by solving a cryptographic challenge to build a valid block. When a solution is found, the winning node proposes a new block of transactions to be added to the chain. POW is done on the premise that the network can remain consistent only if the cumulative computing power of honest nodes is greater than the attacker's computing power. However, the computationally intensive mining and competition leading to high energy and resource consumption are the same reasons that render POW secure. Proof of stake, also known as POS, was introduced as an alternative to POW to reduce energy consumption. The voting weight is related to the assets, aka owned units of the cryptocurrency, which are finite and visible and thus verifiable within the blockchain network, rather than the resource computing power. In proof of stake, transaction validators are chosen semi-randomly through a two-part process. Every validator must invest currencies, a piece of stake, in the network. This amount is locked in the system to be used as a guarantee for the new block. The chances of a validator being selected depend on the number of currencies invested. If this amount is significant, they have more chances to be chosen. When a validator is selected, the validator must check all the transactions of the block and validate them to ascertain they are not fraudulent. When this process ends, the validator adds the block to the blockchain. The reward of this node for validating the block in the fees that are associated with each transaction. POS does not consume as much energy as POW because of the absence of miners. However, unlike POW, the cost of an attack on POS is lower, i.e., POS run the risk of an attack because it will only take a certain amount of coin or stake for an attacker to dominate the network and introduce a fake block to the chain. Presently, the Ethereum blockchain, which has initially adopted a variant of POW, is planning to convert to POS. The figure here shows an overview of some of the other mechanisms. Depending on how the blockchain application and mechanism is designed, different amounts of energy are used for the validation process. A deeper introduction to the topic of consensus mechanisms can be found in lecture 6.3. Consequent to the negative impact of energy on the environment, particularly in the IT sphere, that brought about the indoctrination of green IT as a deliberate effort for sustainability, blockchain as an IT solution should be green. A green blockchain in this sense denotes an environmentally sustainable blockchain that contributes to the mitigation of global warming and the depletion of the environment. Since it has been established that inculcating greenness as a digital prerogative is a viable way of contributing to the reduction of harmful emissions into the environment, a green blockchain should be deemed of topmost importance and ethical responsibility of stakeholders when adopting blockchain solution, especially with the existing global campaign of reducing ICT's carbon footprint by 45% by 2030. To deploy a green blockchain, the following factors ought to be considered. 1. Do I need a blockchain? And 2. If yes, what is the best environmentally sustainable blockchain solution for my project? The ensuing decision support framework from consensus selection is comprised of two distinct parts. The first figure on the left is the primary layer, showing the expanded Wust and Gervais decision tree. More information and other decision trees can be found in lecture 4.2. The second figure on the right introduces the indicative energy consumption, also known as IE-CON chart, showing the link between consensus and their estimated energy consumption based on existing projects. The chart also gives examples of existing projects that adopted the highlighted consensus mechanisms. The IECON chart aims to act as a guide for stakeholders and key decision makers to critically review their projects, its position on the IECON band, and act as a call to action to intentionally promote greenness in their blockchain projects. Conclusion. In the context of climate change and the international and national efforts to save energy and reduce emissions, the application of the proof of work mechanism and the associated blockchain application has no sustainable and ethical justification. When blockchain technologies are designed, sustainability must be ensured. The application of blockchain technology is associated with serious social and environmental consequences and should be applied responsibly. This technology is not suitable for prestigious projects and expects a great deal of ethical reflection from its programmers, marketers, and conceptors. Thank you for listening to this presentation. I look forward to seeing you in the next and last lecture of this module.